Hello, everyone. Thanks for coming. As you were just told, we are going to talk about the prompt engineering and the automatic prompt engineering. But before we begin, you have a chance to open the slides on your own device. I would actually recommend you to do that because some of the code snippets are rather small. And while you're scanning, I will use 15 seconds to do a quick advertising. For those who didn't see, we have a small community booth in the community area, and we invite you to come and talk to us. Why would you want to do that? First of all, we have really nice stickers, and you can pick it up. But in addition to that, later today, tomorrow, and the day after tomorrow, we are going to do the AirPods 4 giveaway. So if you want to take part, please come see us. I guess everyone is ready, so we can begin. First of all, let's ask ourselves, why would we even care about prompt optimization? I guess it was really difficult not to notice that in the last 3 years, I would say, LLMs were a very large topic. Just looking at the NeurIPS 2024 poster presentations grouped by, clustered by the topic, we can see that LLMs take up a substantial portion. However, LLMs are popular not only amongst the researchers, and recently we've also been seeing lots of great tools in this area. And even large companies are stepping in with their own LLM-powered offerings. You probably all know Apple Intelligence, which provide AI native capabilities for iPhone and iPads. However, when we look at how the systems work under the hood, we see something like that. Long, manually crafted prompts with weird instructions like, please do not hallucinate, please output your response in a certain way, etc. And as complexity of tasks performed by LLMs increases, it becomes clear that such tasks require complex prompts. And crafting such prompts is anything but trivial. They need to be precise, well-defined, and non-ambiguous. Which naturally raises the question, can the prompts be optimized automatically given some training data? And the answer is yes. Thank you for coming. I'm joking, so now I'm handing it over to Iryna, who will explain how it can be done practically.
Okay, before we proceed further, we need to make a distinction between simple or single component and compound or multi-component systems. In single component systems, we typically deal with just one prompt. Think of a summarizer or a translator. There is one input, one output, and the prompt is pretty straightforward. Tuning that prompt manually is actually a manageable task. You write the initial prompt, test it, tweak a word or two, and can already see satisfactory results. In contrast to simple systems, compound systems are made up of multiple components that are connected together in a pipeline. As an arbitrary example, imagine a retrieval-augmented QA system. Here, our program first retrieves some documents, generates an answer grounded to these extracted passages, and then summarizes and rewrites the answer. Such multi-component systems are becoming increasingly more popular, and there are a few key reasons for that. First of all, they often outperform monolithic models, especially when designed thoughtfully. In addition, because each module is isolated, we can inspect each step independently. Also, you know that different tasks don't require the same horsepower. With compound systems, you can use different LLMs for different components. For example, you could use a smaller and cheaper model for extraction tasks and a more capable one for reasoning. This allows us to optimize cost-performance trade-offs more efficiently. Finally, such systems give you more ways to ground the model's output with external tools or external data sources. But here is the catch. This added structure comes at a cost. We're no longer dealing with just one model or one prompt. Instead, we have a chain or graph of components, each with its own role and, more importantly, its own prompt. These prompts are no longer independent. For example, a small change in the first prompt can alter the output a little bit, which would result in drastic and unintended side effects in the later steps of a pipeline. Because of these cross-prompt dependencies, manual prompt optimization becomes infeasible. So while compound systems offer important benefits, they also introduce serious challenges in terms of prompt optimization. We already established earlier that there must be a way to approach prompt optimization like a machine learning problem, where we treat the prompt almost like a trainable parameter and optimize it based on some training data. But how exactly can we do that? It turns out that the simplest technique we could use is few-shot and context learning. The idea is very simple. We just put several labeled examples directly into the prompt. For example, to improve text classification, we can apply several text label pairs directly into the prompt alongside a very generic instruction. This way, we obtained a much better prompt without much handcrafting. However, here we have a single component system. Applying the same technique in a compound system is not that straightforward. Why is that the case? Because in multi-step pipeline, we usually only have access to the initial input and to the final output this pipeline produces, but we don't have intermediate input-outputs between the modules. However, we can use training data and a teacher model to construct, trace, and save the intermediate results, which can afterwards be used as few-shot demonstrations. This approach is called a bootstrap few-shot. The idea is as follows. First, we run training inputs through our program. If the output is sufficiently high-scoring prediction as assessed by a specific metric, then we keep this trace. Otherwise, this trace is discarded. This process repeats until a maximal number of good or high-performing traces is collected. Before we proceed with other methods, let us zoom into an important component of this process, the metric. The metric is what tells us whether a model outputs is good enough to be saved as a demonstration. In simple cases, we can use traditional metrics, for example, accuracy, exact match, F1 score, etc. But most real-world applications don't produce simple outputs. They usually generate long-form text, such as summaries, explanations, and so on. For these cases, we can use another language model to score or critique the outputs based on some desired qualities, for example, factuality or some domain-specific requirements like adherence to a brand voice, etc. Let's now look at another method for prompt optimization, which is called bootstrap few-shot with random search. It's based on an idea of bootstrap few-shot method, but it takes it one step further by actively searching for the best combinations of demonstrations. So first, we generate a set of good input-output traces. Then, instead of just inserting these traces into the prompt, we randomly sample different subsets of these traces. Next, each sampled combination is evaluated, and finally, we select the demonstration set that leads to the highest validation performance. You might have noticed that so far our primary approach to prompt optimization was simply adding labeled demonstrations directly into the prompt without doing anything with the instruction. And it turns out that this method is quite powerful. In fact, some studies show that optimizing just the demonstrations can lead to a better performance than optimizing the instruction alone. However, the instructions become more important in tasks with complex conditional logic, and joint optimization of instructions and demonstrations generally yield the best results. So how can we achieve that? One of the most well-known methods is called multi-prompt instruction proposal optimizer, or MIPRO. It is able to optimize both instructions and demonstrations at the same time. First, as in Bootstrap FuShot, we generate a set of good input-output traces. Then, to propose instructions, MIPRO doesn't just rely on language model's internal knowledge, but it grounds the language model with some meaningful context. For example, summaries of the dataset, overview of how the pipeline flows, bootstrap demonstrations, and historical information about prompts and their evaluation scores. Finally, the best combination of instructions and demonstrations is found using a Bayesian optimization strategy. This is a powerful method because it allows to explore a huge space of instructions and demonstrations and pick the combination that works best together. However, MIPRO might still be limited in one key way. It uses a single feedback signal to optimize all modules. That makes it difficult to improve prompts precisely. The optimizer doesn't know which module is responsible for a poor performance. Making an analogy with the deep learning, it's like training a neural network without gradients. You just try different things and see what sticks. The concept that might solve this problem is textual gradients. Just like in neural networks, we could backpropagate those gradients to quantify how each parameter contributes to overall loss and provides direction for optimization. Protege mimics this idea by using natural language explanation of what went wrong as textual gradients. It starts by running the current prompt on a mini batch of inputs. Then it uses the first prompt template that instructs the language model to describe problems which could have led to those mistakes. That response is our semantic gradient. It points in the direction of what is wrong. Then the second language model takes this feedback and edits the original prompt to correct those mistakes. This loop then continues recursively until the most highly performing prompt is found. TextGrad builds on the core idea of Protege, but it allows for systems of arbitrary depth and multiple trainable variables per prompt. According to some benchmarks, TextGrad can be on par or even better than Bootstrap FuShot with 8 demonstrations. Now that we covered the essential theory, I would like to hand it over back to Oleh, who will walk you through available prompt optimization frameworks and more practical code examples.
Yes, so when it comes to the prompt optimization frameworks, without any doubts, the most popular one is DSPy by Stanford NLP. As their own motto says, it's used for programming, not prompting language models. And indeed, in DSPy, the prompts are completely abstracted away from the users through a concept known as the signatures. A simple signature might look just like this, which is just a string. By looking at it intuitively, we can understand that we want to have a question as an input and an answer as the output. In addition to that, our answer should be a floating point number. To test that it works, we can build a very simple program where we initialize a predict module with our signature and then call it by passing a question, what's the average weight of a cat? We will talk more about modules a little bit later, but for now we can see that we obtained the answer 4.5. It's a floating point number, so our signature works as expected. However, in some cases, expressing our problem as a single string signature might be not realistic. For example, what if the input or output fields are not self-explanatory, or you want to explicitly provide the initial instruction? Fortunately, it can still be easily achieved in DSPy by using class-based signatures. Here we have a more complex signature where we want to check the faithfulness of some text given some context. The model should produce its verdict as a Boolean value, but in addition to that, we also provide a list of supporting evidence. In such a signature, an instruction is passed as a doc string and the specification of the input and output fields as attributes. As you can see, the fields also have the optional descriptions. So such class-based signatures can be used in exact same way as the string-based signatures would, and in fact, all kinds of signatures get internally converted into signature objects anyway, so it doesn't really matter what you use. But you might be wondering where or how these signatures are being used under the hood. And to answer this question, we can have a look at the raw data that is being sent to the LLM. And here we can see that our signature got automatically transformed into a rather long system message. It starts with the specification of the fields, then the general description of the format, and finally the instruction itself. So now that we understand how signatures work, we can talk a little bit more about modules. Modules are the basic building blocks in DSPy, and if you have ever worked with PyTorch or other similar frameworks, you would find a lot of conceptual similarities. So DSPy supplies several pre-built modules out of the box, and due to the time constraint, we won't be able to look into all of them, even though there are not that many, but we will have a look at just two. We are already somewhat familiar with the predict module, which is the simplest module in DSPy, and it simply executes the signature without any modifications. A slightly more complex one is a chain of thought module, which ensures that the model produces some reasoning before the final output by modifying the initial signature and adding the additional reasoning field, reasoning output field. And exactly like in PyTorch, we can create our own custom modules using the primitive ones as the building blocks. Here we built a chain that first translates and then summarizes the text. The final two components we need in order to optimize our model are teleprompters and metrics. Again, drawing the analogy with deep learning frameworks, a teleprompter would roughly correspond to an optimizer which iteratively adjusts the demonstrations and the instructions of all the submodules. Once we have a module that we want to optimize and the teleprompter initialized with some metrics, we simply call the compile method, which is the equivalent of fit or train. So to sum up, in DSPy, you would usually create custom modules using the pre-built ones as basic building blocks and the signatures as abstractions over prompt templates. The custom modules would then be optimized by a teleprompter based on some metric. The next framework we will look into is TextGrad, which is also the official implementation of the TextGrad method presented in the first part of the talk. Unlike DSPy, TextGrad is a relatively small framework and also a low-level one, so it provides only a handful of primitives out of the box. The first important concept in TextGrad is a variable, which is either a complete or a partial prompt template that can also be optionally optimized by setting the respective value of requires grad attribute. To use the variables, TextGrad provides a built-in black box LLM module that takes one variable for the system message in the init and another one for the user message as an input. Now, in order to optimize our instruction, we use the same syntax as we would in PyTorch. First, we calculate the loss, where the loss is just a feedback from a judge LLM. Then we call backward on the loss, and then step on the optimizer. And basically, this is more or less everything that needs to be known to work with TextGrad. It's very simple and intuitive, but some things cannot be easily implemented out of the box. For example, what if you wanted to optimize only a specific part of the prompt while hard-coding the other one, or provide some few-shot demonstrations as in DSPy? Which brings us to the last framework for today, called ADALFlow. Overall, it can be viewed as an extension of TextGrad, but with many elements taken from DSPy. Given that we don't have that much time left, we will only go through the most important differences between Adelflow and TextGrad, but without digging deeper. Firstly, in TextGrad, we had variables, and in Adelflow, we have parameters, which is the same thing, but importantly, now we have two types of parameters: prompts to hold textual instructions, and demos to hold the future demonstrations. These parameters can be used in explicit prompt templates. Hence, the prompt template can have both a dynamic optimizable part, our parameter, and also a static hard-coded one. The functionality related to a certain pipeline can be encapsulated in a component, which is an equivalent of a module. Now, in order to optimize our component, we first need to wrap it into another ADL component. ADL component is a special type of component which expects the component we want to optimize, evaluation function, and the loss function. And then we can finally pass this ADL component to the trainer and call fit on the trainer. This might look a little bit too verbose, but at the same time, it's really not that difficult from what we've seen in other frameworks. So to sum up, Adelflow is a very feature-rich framework that contains or combines the ideas from TextGrad and automatic visual learning, like in this SPY, but in my opinion, it's a little bit too verbose, which is not necessarily a bad thing, but it might potentially imply a steeper learning curve. Now we are done with the frameworks, and we can go back to our initial question: is manual prompting dead? And as always, the answer is not that obvious. Without any doubts, automatic prompt optimization brings many benefits. It is fast, it's simple, and in many, if not most cases, it's still cheaper than manual effort. Additionally, this optimization procedure can be easily repeated in case the target LLM changes. However, there are also some limitations. First of all, the underlying prompt optimization procedure still depends on the hard-coded, manually crafted meta prompts. And those meta prompts are not guaranteed to be optimal for your specific task. In addition, by using the automatic prompt optimization, you are still bound by the reasoning power of the LLM, which might be limited. Therefore, probably, it might be too early to declare the death of manual prompting for now, yet automatic prompting is a viable alternative, and we definitely encourage you to try it yourself. And finally, if you want to try it, but you don't want to learn a new coding framework just to do that, at Dataforce, we have recently launched the Dataforce Studio, which is a data platform. It's open source. And we have automatic prompt optimization as one of the tasks. So it is now live. It's open source and completely free to use. So we would really appreciate if you could start it on GitHub or provide your feedback. Again, I remind you that we have a booth in the community area, so please come and talk to us, and we have AirPods for giveaway. And that was it from our side. Thank you for your attention, and we are ready for your questions.
Oh, that was fantastic. Perfect timing. So there's a microphone in the aisle over there if you'd like to start lining up there if you have a question. Sorry, it's a bit of a walk for you. You might still be the first.
Thank you so much for your talk. I was wondering about two practical considerations. One is, how well does this work if you want to change the language model? Is it generally okay to still be using the prompt, or do you have to go over the routine again? And the second one is, how intensive is this kind of optimization? How many LLM calls are we talking about for such an optimization procedure?
Okay, so I didn't really get the first one. What exactly do you mean by changing the LLM?
Well, better LLM models are coming out all the time. And if you want to use a newer, better one, do you optimize the prompts from scratch? Or is it generally okay to keep using the previous version?
Okay, so It's really difficult to answer this question because it depends. I would say in many cases it is still okay to use the previously optimized prompts. However, this prompt optimization procedure is really, really easy to repeat. Therefore, it's one of major advantages of automatic prompt optimization. When the underlying LLM changes, you just retrain it. But it should be okay to use the previous prompts as well. Regarding how intensive it is, it also depends because there are different methods, but it can be quite intensive. So it can be hundreds, thousands, tens of thousands of calls. It can become quite expensive. However, when you calculate how much time a data scientist would need to sit and adjust everything manually, you would realize that it's actually cheaper anyway.
Thank you so much.
Thank you.
Hi, thanks very much. I'm just asking, as somebody who's very ignorant, who just came here, has never done any prompt engineering, and kind of didn't understand a lot of what was said. Could you give a worked example of what exactly is happening when you're optimizing the individual prompts? Like, I don't understand how the text of those prompts is being changed. Are they provided beforehand and then selected between? Just natural, like, work through.
Okay, so basically you can provide the initial instruction, but you don't have to. And there are two ways you can optimize the examples. And in this case, the instruction is not being optimized at all, but you add some demonstrations before the instruction. In addition to that, you can optimize the instruction itself. And when you are optimizing the instruction, the new instructions are being generated by another LLM based on some.
I don't know what the words demonstration or instruction refer to.
Okay,
so
demonstrations, it's basically an example. You have this input, and when you have this input, you provide this output. So it's, imagine you are talking to ChatGPT, and you just say, okay, when you see this input, the output should be like this. And based on these demonstrations or examples that are provided directly into the prompt, it can...
So a demonstration is a synonym, for example?
Yes.
Or, okay.
Go ahead.
Thank you for your very inspiring talk. My question is, how do you avoid overfitting? So what is your equivalent to a dropout layer?
Okay, the equivalent of a dropout layer. To be honest, I'm not sure. I'm pretty sure in the SPI you can do something like a dropout layer if you really want to. Yeah, generally, if you don't provide the specific examples, if your data set is really, really limited and you know that it's not generalizable enough, don't provide the future demonstrations, just try to optimize the prompt itself, and then it should regularize it in a way because it doesn't see exact examples. But yeah, it's a good question, and yeah, obviously, as with regular machine learning, you also have a test set. You should test it on the test set to detect the overfitting, but if the overfitting happens, it's not that easy to counter as it would in regular machine learning.
So we have 1 minute left if you think it's a quick question.
Yes, a very practical question. Have you compared the performance of one of the methods compared to manual prompting? And which one is better to use to optimize your prompt?
So how do we compare the performance of an optimized model versus the...
like a human?
Yeah, I mean, it's really easy because it doesn't matter whether it was automatically optimized or optimized by human. In the end, you should have an evaluation data set and a certain evaluation metric.
Yeah, my question is more like, have you observed like better performance from like an optimized prompt from your methods compared to like a manual prompt?
Okay, so with manual prompting, in a lot of cases, you can still achieve better results, but the question, it's really a business question. So does it matter if a human spends like another 1 or 2 weeks trying to optimize an instruction to get, let's say, additional 1%, or it's fine if it gets optimized automatically in half an hour and it's almost as good? Yeah, and when the new model is released, again, you don't know whether your old prompts are good enough or not. As I said earlier, probably they're still okay, but with this automatic prompt optimization, you can always repeat the whole optimization procedure. But yes, as I said, with automatic prompt optimization, you are still limited by the reasoning power of the LLM when it optimizes the prompts. Therefore, theoretically and practically, a human can still achieve better results, but with a lot more effort.
Thank you.
Okay, I'm afraid that's all we have time for.
You can find us near our booth, and we can talk there.
Thank you very much.